Ladies and gentlemen, I'm Dr. Nakashima of the Chemistry Department. It's a time to start today's seminar. I will chair today's seminar, and today we have very special guest from Korea, Professor Yang-hee Lee. He is a leader of nanotechnology in Korea and worldwide very famous professor. First of all, I'd like to introduce his profile briefly. And Professor E has been a full professor of physics department at Sungkyunkwan University since 2001. And he received a bachelor's degree from Chonbuk National University and a PhD from Kent State University in Ohio, all in physics. And then prior to joining present university, he was a full professor in physics department of Chonbuk National University since 1986. His experience in research includes visiting scientists at Ames Laboratory, Iowa State University, visiting scientists at IBM, Zurich, Switzerland, visiting professor at Michigan State University. Currently, he is head of Department of Energy Science, world-class university at Sungkyunkwan University. And he is associate editor of European Physical Journal, Applied Physics. And he is leading several national research projects in Korea in CNT field effect transistor area, flexible transparent conducting film, CNT aluminum and CNT liquid crystal composite, solar cell, and super capacity batteries, including the previous national research laboratory. He was awarded the first Sungkyunkwan University Fellow in 2004. Science Award from Korean Physical Society in 2005, and more. He has focused on understanding the fundamental properties of nanocarbon, such as carbon nanotube, graphene, and graphene oxide, and their application to various devices. His application to device covers field emission display with carbon nanotube field effect transistor, graphene transistor, flexible transparent conducting film, supercapacitors, secondary batteries, gas sensors, hydrogen storage, third generation, solar cells, and metal, and more. And he has published more than 300 scientific papers with high impact factors. And he has also 150 patent. And his total SCI citation number reaches over 12,000. That's quite high. And his so-called H number is currently 47. This is also quite high, very high. I hope you understand. Okay, so it's a time to have his lecture. The title of his lecture is Carbon Nanotube versus Graphene in Electronics. Professor Lee Sensei, onegaishimasu.
Should be good. Okay, thank you for the introduction. I'm Yang-hee Lee from Sungkyunkwan University, Korea. It's really a great pleasure for me to be here to give this talk. This is the first time actually to be in Kyushu University. I've been in Japan many times, but not Kyushu University. I saw, when I came here, I saw this sign, Kyushu Daigaku 100 years. This university has a history of 100 years. I really congratulate all you guys. So Sungkyunkwan University in Korea, actually Sungkyunkwan name came from very old history. I think some of you guys know Korean language was created by one great King Sejong. And King Sejong actually initiated this Sungkyunkwan Academy in 613 years ago. So this one we called, we have this longest history in the University of Korea. So, but it's difficult to pronounce. We usually call it SKKU. It's easier for you probably to remember. Anyway, as Professor Nakajima introduced, we have also one department, world-class university program, which is similar to this WPI. We invite foreign professors in our department. We also provide all the lectures in English. So this is actually a new trial system in Korea to globalize our society. I usually like to start with this images. This is the one picture drawn by one of previous student. Actually, this guy, who's an artist, drew something by looking at this egg. Of course, this guy doesn't know anything about what's inside an egg. But as a scientist, by just looking at an egg, you probably cannot draw this bird easily. But of course, you can do something systematic, like shining light, or even shaking, or even using some X-ray to investigate what's going on inside. But anyway, even though we are scientists, we somehow rely on our imagination still. I think imagination is a key ingredient in basic science, particularly in our nanoscience and nanotechnology, which is still premature compared to other research area. We still rely on imagination in many things. So this actually symbolizes that. So don't forget, we have to use our imagination in our science. This is actually my group. We have actually many guys in our laboratory. We have almost 40 guys, 40 students, masters and PhD, all working together in carbon nanotubes and graphene. I bet the audience actually came from many different disciplines. So let me introduce something. So I'm going to talk about these carbons. This carbon, actually, if you start from this graphite, which is this black material, this is what we call three-dimensional material. And usually this pencil is composed of this graphite. And this is what we call sp2 hybridization. Whereas this diamond, the same, composed of carbon, but in this case, whereas this one is completely black, this is completely white. Of course, with some impurities, you see these beautiful colors. It makes a woman happy. And but this is what we call, again, 3D structure, but electronically, this is what we call sp3 hybridization material. Whereas this kind of C60, which was found in 1985 by Smalley, Kroto, this one actually has a mixture of this sp2 and sp3. This sp3 guy has 4 coordination in its neighbor, whereas this guy has a 3 coordination. This guy, although it has a 3 coordination, because of these pentagons and because of these hexagons are similar to graphite, whereas this pentagon, if you look at the bond angle, is similar to this diamond. So this is a simple mixture of sp2 and sp3. But we found a way of producing these materials. This is what we call zero-dimensional material. But of course, in 1991, people also found this special geometry, like a tube type, what we call carbon nanotubes. This is a simply one-dimensional structure. So we have basically carbon rolled up, very long in size. but the diameter is in terms of nanometer scale. So this is very unique material. And this material has attracted a lot of researchers actually in many different research areas. So the number of papers published so far is more than 10,000 papers, I bet. Yeah, do I have a correct number? Right? It's about, no, more than 100,000. 100,000, I'm sorry. One order difference. So it has been very popular. Of course, you know, for instance, in Korea, we are using this material for many applications in industry. And recently, in 2004, graphene was found. Of course, this is nothing much different from this graphite. But this one is all three-dimensional material again. I mean, stacked together. But this one is a single graphene layer. So this single layer has special characteristics of high electron mobilities. So people are fascinated by this material. Of course, this is simply two-dimensional structure. So people can do easily science. That's one thing why people like it. It's easy to understand. Anyway, people nowadays are working on this graphene. And of course, there is another category of this graphite material. One, we call it graphite oxide. This is basically, you oxidize this graphite, and then once you oxidize, these guys can be easily dissolved in water, and you can simply exfoliate these layers one by one, which has similar structure of this graphene, but still different because these are all oxidized. These has all different characteristics. So with all these different carbon allotropes, we have now choices. What is the best? What can we use it for? So I like to focus on particularly these carbon nanotubes, and recently this hot material, graphene. Because I have been working with carbon nanotubes, many people ask which one, I mean graphene or carbon nanotube, which one's better? I have been asking these questions, and I'm actually writing one review paper in Advanced Functional Material to compare this carbon nanotubes and graphene in terms of electronics applications. So if you look at this basic properties between these two materials, for instance, I mean, the different type of structure, single-wall carbon nanotubes, double-wall carbon nanotubes, even multi-wall carbon nanotubes, we can all synthesize these different materials. We can also prepare single-layer graphene, double-layer graphene, triple-layer graphene, very similar. Okay? All the fracture strain, Young's modulus, these mechanical properties are very similar between these two structures. If you look at these numbers, I mean the performances of these two structures, all the materials very similar, because basically it's a carbon. One is a simply rolled structure, the other one is a flat structure. So there is almost no difference. But of course, practically there is a difference because in some cases, graphene is more practical, I mean easier to apply or to use than carbon nanotubes and vice versa. So I'm not going to go the details of the fundamentals. In terms of processability, okay, if you look at the morphology, carbon nanotube is simply black powder, dirty powder. So if you go to the carbon nanotube laboratory, usually it's dirty. So black dust. Graphene, of course, if you talk about this large area graphene, of course, it's a different story. But if you talk about this graphene powder, it's again black, dust. So it's the same thing. So in order to use these materials for some applications, we have to dissolve these guys in some solution and prepare, for instance, a film or transistor. So in terms of that, these are all bottom-up approach. There's no difference. We have a hard time in each in optimizing the conditions for the best use of the applications. And but if you look at the individual nanotube, for carbon nanotubes, we have a hard time in aligning them in some direction, for instance, for the application purpose. And graphene, nowadays we can produce a single layer graphene, large area on substrate. So you can simply use this large area graphene you can probably use the top-down approach to make each transistor individually in principle, which is completely adaptable in current semiconductor industry. This is one thing the Korean, particularly the Korean industry is paying attention to this material because there is a possibility. But other than that, I mean, basically the properties are very similar. So the question is, who's better? Either Superman or Spider-Man. But my viewpoint is not this competition because I'm using both materials. It's like Sebastian who has two strong guns. Of course, then the question is how to use these guns, okay? If you know how to use it, of course, it'll be very powerful. But if you don't know how to use it, it's useless, right? So the question is how to use these materials. So I'm going to discuss this in terms of two applications in electronics. One is transparent conducting film. The other one is transistor. Transistor and transparent conducting film is actually a very big issue in Korea because these are all related to semiconductor industry. Okay, let's first talk about this transparent conducting film. So if you have this film, what can be used? For instance, we can use this material for touch screen. I think you have your cell phone, and you can use this touch phone. Of course, this is made by nowadays indium tin oxide material, but we know indium is a very limited natural resource. The price is going higher and every year, and of course, China is the major source of the material. They are trying to increase the price. So Korean industry is very much concerned about this material. They look for some other alternative. So if you have that, you can have this touch screen, and in the future, of course, you can use this material for some rollable display or e-paper, whatever can be bendable. Of course, then the question is the performance of the film. For instance, if you have 500 ohm per square at 90% of transmittance, you can use it for a touch panel. If you improve the characteristics of this film, and then you get this like a 30 ohm per square, indium tin oxide, the best quality of indium tin oxide is like 10 ohm per square. So we cannot compete at this moment with ITO. But if you go for a flexible display, then there is a different story, okay? Because ITO cannot be bendable. Anyway, so if you improve this conductivity of the film, then you have many different areas for applications. So let's talk about this transmittance. If you look at this single layer graphene, the transmittance is almost 97%. So each single graphene layer absorbs only 2.5% of light. Whereas carbon nanotubes, still okay. The difference between this, because this single carbon nanotubes has a thick layer, but basically they are quite inert over this wavelength. Whereas this ITO has a very strong absorption near UV region, which is another serious drawback. And then you have also this wavelength dependence in the visible range. So this is a problem. And of course, at this moment, this one has the lowest resistance, so people still use it. But again, when we test this bending stuff, you try to bend, and you do it several times. What happens? This guy, because it's inorganic material, it cracks. So the resistance increases suddenly with this. Whereas this carbon nanotubes or graphene has no changes at all. So this is the room where this carbon-based material can play as an important applications in future flexible display. Now, how do we prepare the films if you have this powder? Of course, as I mentioned, you can use many different methods using this liquid approach. You have to disperse this material in liquid and then spray them onto the substrate, and you get the film. Many different methods. We are using spray method simply because it's simple and you can make a large area and with high uniformity. So the procedure is very simple. You dissolve this carbon nanotubes or graphene powder into the solution and sonicate, and some of the aggregated CNTs or graphene, we don't want to use it, so we can remove them by the centrifugation. And then we have the CNT or graphene ink, and then spray them onto the substrate, and then we simply measure it. So this is one typical data, sheet resistance as a function of thickness. Okay, if you increase the thickness, of course, the resistance decreases. But if you increase the thickness, of course, the transmittance of the film decreases as well. So these two are the trade-off, sort of. So you can also plot this one in terms of this transmittance and sheet resistance. We always have this curve. Okay. So for instance, for touch panel application, we need a 90% of transmittance, and the resistance should be like 100 ohm per square, 100 ohm per square. Okay. But still, this carbon nanotubes cannot meet this criteria. So you have to do something, and actually what we did is we dispersed CNTs using this surfactant such as SDS or NADBS, because SDS is basically insulator surfactant, and we want to remove them. We remove them by simply acing by nitric acid in this case. You see by a simple nitric acid treatment, this sheet resistance is improved quite significantly, independent of the thickness. So this is a simple way of removing SDS. Usually people believe SDS can be removed by simply washing in water, but that is not the case in this, because nanotube in this case is simply a random network, and then they are entangled each other, including this SDS. So by simply washing, it doesn't work. So you have to do something, and then we found this acid treatment is a very good approach. Actually, we try to, I'm going to just skip this one, okay? But what we found, other than just a simple acid treatment, we actually had a further doping treatment. For instance, using gold chloride, we are able to dope the carbon nanotubes and then improve this conductivity further. So this is the result. For instance, by using this gold chloride treatment, you see after this acid treatment, and then we further treat this by gold chloride, you see the improvement of the sheet resistance again, at least about 30% for each case. So with this kind of improvement, we can now use this film for touch panel, even for some display applications, small size. Actually, we have one Korean project working together to develop this film now for real application of touch panel. Well, this is one approach. Another approach is to use this graphite powder. Of course, as I mentioned, we can create graphite oxide by oxidizing this graphite, and this interlay distance is expanded to almost twice from this originally 3.4 angstrom. This becomes like more than 6 angstrom. So this was done by having some chemical functional groups on the surface of graphene sheet, and this is a very well-known technique. And then once you do that, this guy can be dissolved well in water, and then we can simply dissolve them in water and then prepare the film. Of course, during this process, we can have a reduction process to remove some of the oxygen groups, because oxygen functional groups basically increases the resistance of the graphite oxide. So to some degree, we have to remove them while we are keeping this solubility of the powder in water solution. And then we can simply measure this sheet resistance again. Whatever we do, the technology we developed in our carbon nanotube research, we apply the same thing here. Of course, we see this improvement. But if you look at the absolute value, still this is far from the real application. So with this approach, the graphite powder, there's no way for us to obtain high quality conducting film using graphite oxide approach. So we tried to some degree to improve this quality. For instance, once we have this graphite oxide, we can simply exfoliate this film, not in solution approach. In this case, simply just a heat treatment at 300 Celsius degree. And then you can simply exfoliate all these layers one by one. Still some functional group exist. In this case, we can remove them by having heat treatment, again, very high temperature, like 1900 Celsius degree. And then we can have very clean graphene, individual graphene layers. So this is actually what we developed in the lab. Again, even using this approach, in the case of pellet formation, the conductivity is very similar to the existing graphite, which is very good. But again, if you make the film, again, we have still problems, not even close to the CNT. So from my point of view, unless you do something very different approach, there's no way using graphite oxide to get these highly conductive films, which meets this technological criteria. So this is one reason, again, for us to develop this large area graphene from some solid approach. Of course, people used this silicon carbide and simply have a heat treatment at high temperature. And this carbons out diffuses to the surface of this silicon carbide, and they form a graphene layer. But again, to detach and to use this is kind of troublesome. And of course, this uniformity in large area is again a problem. And of course, people try to use some catalyst material like nickel. We also did the same thing. And we were able to get graphene, large area graphene. But the problem is, again, the uniformity. And from point to point, we get single layer, we get double layer, we get triple layer, but it's not uniform. We cannot control it. It's very difficult to control. There is a reason why you cannot control it. It's because of this carbon solubility in metals. If you look at this, for instance, nickel. Nickel has quite high carbon solubility. So what happens during this large area CVD process, carbon first melts into this nickel layer, and then during the cooling, this carbon out diffuses again because of the limited solubility, and then form this graphene layer. But because of this high solubility, we cannot control the number of layers. It's difficult to control the number of layers. But if you look at this copper, copper has very low carbon solubility. Of course, there is no guarantee that you will get a single layer. But somehow, by chance, if you use copper, this is a perfect condition for having a single layer graphene. Actually, everyone can succeed in this. For instance, you can simply have this copper foil, large area, you can simply roll up and then insert into this quartz chamber. And you simply supply the hydrocarbon gases at high temperature, and you will get this graphene formation on the surface of this copper film. So this is what we get large area graphene. And again, the problem is once you have this large area graphene, so what are you going to do with this? Can you use it for transparent conducting film? Of course we can. We can simply transfer this large area graphene using this roll-to-roll process. For instance, we have this PT film, which is completely transparent. And we can simply coat this PT film by some binder, thermal binder. And then you simply roll them together to have this, this PT, graphene, and copper together. Okay. So we stick them together, and then we simply dissolve this copper layer by copper etchant. Then you have graphene on PET, which can be used for transparent conducting film. So this is a method people developed. And if you do that, then you can see, okay, the transmittance again 97%, which means you have single layer graphene. And another evidence is this Raman spectroscopy here, this G band and G prime band. This is again characteristic of single layer. You can also identify them from this TM and also electron diffraction pattern. Again, the uniformity in large area, for instance, uniformity in electrical conductivity. Well, we checked that, it's like 30 centimeter by 20 centimeter. You see this fluctuation is like 10%. So it's quite acceptable. The point is, with this approach again, what's the sheet resistance? The best value we can obtain in the laboratory is like 300 ohm per square, which is still far from the real application. So what we did is, okay, let's, because we are able to create one single layer, large area graphene, we can simply layer by layer doping and transfer again. So you can have this gold chloride doping, each layer. You have single layer transfer and then dope by gold chloride, and then another layer transfer and then dope, and then like this one. You can repeat many, many times to this and to create some films, okay? So with this one, you can see we can achieve very low resistance, which is quite comparable to that of carbon nanotubes. So if you combine them together, you can see this is originally single carbon nanotubes, and we have this nitric acid treatment, and we have this gold chloride treatment, and then we have this single layer, double layer, triple layer, quadruple layer graphene, and we again doping. So you see the sheet resistance is reduced almost similar level to the best carbon nanotube case. So this way we believe, okay, in terms of this performance, fine. Graphene can be also used for touch panel. So if you compare these two properties, almost same. But of course, graphene has one serious drawback in terms of process, this transfer process. This is really a headache. If you work with a graphene, transfer a large area graphene onto another substrate is really a headache. And of course, CNT, you have CNT powder, you have to dissolve in some solution and then make the film. This is again involves a quite complicated process. So we have one thing good, one thing bad, but it's up to your choice. Now, let's move on to transistor application. When we try to use carbon nanotubes or graphene for transistor, we have many different issues. One is, what is the mobility? Of course, the mobility for single nanotubes and graphene is really high. Compared to any existing material, this is the highest. Fine. What about the on-and-off ratio, which is crucial for switching the device? Carbon nanotubes is pretty okay. Graphene, to have a high on-and-off ratio, you have to make a nanoribbon. Means you have a graphene, and you have to make this width very, very narrow, less than 10 nanometer, which is another technical barrier for this use. So that's one problem. And another real practical problem is on current level, which we don't usually pay attention to, but I'm not going to mention that one. And then another one is this contact. When we use carbon nanotubes for transistor application, we have to connect this guy using some metal layer. And then this metal and semiconducting carbon nanotubes form a Schottky barrier. Somehow, we had a hard time in understanding this phenomena, even nowadays. So this is actually trouble. And then also, if you make 100 or 1,000 devices, are they working all the same? And of course, the is strongly arguable. And again, the processability. So if you work with an individual carbon nanotube, of course, this is perfect. High mobility and high on-and-off ratio, similar to silicon device, but the mobility is huge. So definitely, with a single carbon nanotube, transistor works perfectly. But the question is, we're not going to make a few devices. We are going to make millions and billions of devices, right? For that purpose, we have to align them in a certain way, which is impossible for us to do. So one practical way to realize this transistor is random network transistor. So people try to use this random network CNT. But in order to make this random network CNT, we have also many other problems. One big serious problem, of course, one big problem is in CNT powder, we do have a mixture of metallic carbon nanotubes and semiconducting carbon nanotubes. Of course, for active channel, we need a semiconducting carbon nanotubes. But this is a mixture, so we have to select or separate the semiconducting nanotubes from the metallic ones. So for that purpose, people use what do you call this, Boyan density gradient method. So basically, you dissolve these nanotubes in solution and create some buoyant force. And because of this different reaction of this metallic, either semiconducting one or metallic ones with this surfactant, some are floating and some are precipitated. So by using this technique, you can actually separate metallic tubes or semiconducting tubes. This is a well-known chemistry approach, and people have succeeded. For instance, if you look at this absorption spectroscopy, this is a semiconducting peak. This is a metallic peak. See, this guy does not have this metallic peak, but only semiconducting peak, whereas this guy has no semiconducting component, but only metallic component. So you can actually separate them, okay? And the separation yield nowadays is quite high, more than 95%, which is excellent. And some people try to have a mass production using this approach, using this microfluidic channels. And then also this Japanese group, they use this agarose gel to produce the separated, large amount of separated nanotubes. Kataura's group. So in terms of the separation, well, okay, this is solved. And then another one is actually assembly. Of course, assembly, we can use this solution approach. We can make just spray this CNTs onto the film substrate and then make this random network CNT transistor. And you can realize, this nanotube transistor with reasonable on and off ratio. And if you carefully enough, you can actually make all the device works. So the yield of device is almost 100%. So this is reasonable. Another approach is not to use the solution approach. We can simply grow or synthesize carbon nanotubes on the substrate, silicon substrate, for instance. And then you can simply transfer these guys onto the desired substrate. Okay? And then you see in this case, if you make the device, somehow, although there is a chance of having metallic nanotubes, if you make the device, all these guys works very well. So there are several reports already that using this CVD approach, mostly semiconducting nanotubes are produced. This is another advantage. We don't know why, but I mean, it works. And then there is also another approach people use to align these nanotubes from growth. For instance, they use this sapphire or quartz substrate. This one has a special direction, crystal direction. and then by simply spraying this catalyst onto it, and then you see carbon nanotubes are perfectly aligned on this preferential direction. So you can see this aligned carbon nanotubes, and you can actually use these individual nanotubes for transistor. But again, some portion of metallic tubes exist. So you still have this relatively low on-and-off ratio. But of course, in principle, you can burn them out. But again, this is not easy approach. And many people also demonstrate the realistic device, in this case, a ring oscillator, using 108 thin film transistors. This is also done by this Mistani group. And you can see this practical demonstration of the ring oscillator. So the research is in this area is quite mature with a single carbon nanotubes. Now, one serious drawback, again, even though you have the semiconducting nanotubes, is doping control. We need an N-type or P-type to have this CMOS devices. But unfortunately, carbon nanotube shows this ambipolar, or in ambient case, is a P-type transistor behavior. So we spent also some time in controlling this doping type. Now we are able to get this N-type doping using some NADH, this biological material, or you can use some chemicals, for instance, viologin in this case, and you can also see the device works perfectly. This is originally P-type, but after doping, this one changes into N-type. So we can control N-type or P-type, but these are very stable in air, actually. This is the one very important point. And we can use this technique, and then you can actually get this random network transistor again by this inkjet printing, and then you can have this P-type, and you can also have this N-type. By combining these, you can make many logic circuits. So no problem, we can do that. Of course, there are many other methods we can realize this transistor using different approaches. I'm not going to discuss all this because of the time. One thing I like to emphasize, although we are able to control now, okay, the semiconducting nanotubes can be separated, and doping can be controlled, either N-type or P-type. Still, we have to use this metal electrode to fabricate the device. As I mentioned, we sometimes don't work, we sometimes don't understand this one very much. So we actually try some different approach. For instance, we developed graphene. Graphene is highly conductive. So we try to use graphene as an electrode instead of metal electrode. But carbon nanotube, again, is active channel material. Okay? In this way, okay, one serious drawback of using conventional metal electrode is this one. So we have this gold electrode. Gold is typically used. But look at this one. You have this gate voltage sweeping, 5 volt, and then you increase this gate voltage sweeping, and then large hysteresis. This is actually a serious drawback in terms of this device operation. And we cannot avoid this using this typical metal electrode. But if you use a graphene instead of gold as an electrode, we first have the CVD grown graphene and then make a pattern similar to any kind of approach using photolithography system. And then we simply deposit these nanotubes onto that as an active channel material. So we have source, drain, and gate, all graphene electrode, but carbon nanotube is an active channel material. With this one, somehow, if you look at this one, now we try to increase this gate bias sweeping, and then no further hysteresis increased. This is one great advantage of using graphene as an electrode. I believe this is a very important procedure. And actually, with this approach, you can get many good properties of the transistor. So the future direction should be going like this one by combining graphene and also carbon nanotubes together. Now, of course, the question is, can we just use a graphene for transistor? Of course, we can in principle using this top-down approach. We have large area graphene. We can chop them into small pieces and then make this small size graphene transistor. Of course, people have used originally the solution approach. For instance, so the idea of using graphene as a transistor, if you make a very small channel width, this is a channel width, and this is the energy gap of the graphene transistor. So by decreasing this channel width, you can see this energy gap opens. Usually graphene is a metal, right? So you cannot use directly for transistor. You have to make a very small width of graphene so that the electron is confined along this direction. So we have this electron confinement effect that opens this band gap. By decreasing this width, of course, you can increase this band gap. But look at this number. 10 nanometer width, you have 100 milli electron volt. Now, typical single carbon nanotubes, which has a diameter of 1.4 nanometer, has a band gap of 0.7 electron volt. We still believe this is too low, okay, compared to silicon. Silicon has an energy band gap of 1.1 electron volt, which is fairly enough to operate at room temperature. But this one, with 100 milli electron volt, there's no way to use this one as a transistor. That means you have to go further, less than 10 nanometer. Okay, 5 nanometer, yes, we can have reasonable energy gap. The question is, can you do that? Of course, we can make it in the laboratory using E-beam lithography if you are good, if you have good hands, okay? Not always. If you must be lucky to get this one. But if you take that to industry, there's no way to use it, okay? So the question is, can you really make this nano ribbon with less than like a 5 nanometer? So this is one work done by Stanford group, Hong Ji-dai. They actually use graphene powder and sonicate them and exfoliate them one by one. And then you just spray them onto the substrate, and then you will see you have some chance of having very narrow ribbon. Okay, like this one. And then you can connect this source and drain electrode, and then measure this, and then you see this high on and off ratio by chance again. So yes, it works in principle, but you cannot adapt this technology for real industry application. So in real industry application, you have to have some systematic way of producing nanoribbon. But again, no way. I mean, in this case, the best energy gap is like 0.2 electron volt. I mean, 200 milli electron volt. In this case, you have to have less than 10 nanometer, which is very difficult. But even though you are able to make nanoribbon with less than 10 nanometer, and then what happens that when electron goes through this one, electron can be scattered easily by this edge state. Okay? So there's no guarantee you can get this high mobility anymore. So this is again the trade-off phenomena. And we have to find some good way of making this nanoribbon, but without causing this edge scattering. This is an open question for all of us. So I mean, in Korea, we do have now a big national project to be launched soon with this graphene. But I'm very much skeptical. to get this kind of industrially adaptable technology. It's very difficult unless we have some genius young students to invent this new method. There's no hope in this moment, at this moment. So of course, people try to, even in our group, try to use carbon nanotubes. And then you simply open the etched half of the nanotube. And then, of course, you can have this graphene ribbon. Of course, then you can have some improvement. But the point is this a really good approach to make in terms of this transistor application? Because you are creating edges, edgy dangling bonds, which creates the scattering of electrons. So then reduce this mobility. So if you want to use this method, you better use a carbon nanotube directly, because carbon nanotube itself does not have these problems. Nanotube itself has high mobility and also high on-and-off ratio. So this is not a good approach anyway. So if you compare all the device properties, like the mobility, both carbon nanotubes is okay, but when we make a nanoribbon, then mobility drops significantly because of this edge scattering. And unless you solve this problem, we are not guaranteed to have this high mobility. On-and-off ratio, yes, if you can make a nanoribbon, you can have a high on-and-off ratio like 10 to the 6th or 10 to the 5th, similar to silicon device. And on current level, graphene has an advantage, because in carbon nanotube, a random network transistor, this is simply randomly entangled. You have many open spaces. So the current that flows through this given area is not very high, whereas graphene is fully covered. So you have a high current expected. So fine. And the contact, well, we can use graphene for contact. For instance, if you use a graphene, large area graphene, and you can simply pattern this nanoribbon using any kind of lithography system. And then you don't have to worry about this contact problem anymore. This is another advantage of graphene, because graphene can be used as an electrode. Also, by making ribbons, you can use directly there as an active channel. So this is a big advantage. And another advantage from industry point of view, to make this random network CNT transistor, you have to use this bottom-up approach, which is not favored by industry. But because you have large area graphene, you can simply chop them up into small devices, which is a top-down approach. This is what current industry is doing. So they have no problem in adopting this technology. This is one big advantage. So that's why Korean industry are paying attention to this one at this moment. So again, so I would say the challenges in carbon nanotubes and graphene, we have two, excellent machine. Of course, the question is how to use it. So far, in terms of this transparent conducting film application, I think both graphene and CNT have room to be used. We are, in our laboratory, we are trying to fabricate one CVD system, this continuous continuous production of graphene in large area by what we call a roll-to-roll CVD process. This is another challenging for us in terms of this application, but I think in principle can be done sooner or later. And Korean government is trying to invest money for this, so I'm sure we'll get something done in the near future. So sheet resistance, well, fine. This is fine. Now, transistor application. As I said, unless you create a new method of having nanoribbon, where this width is less than 5 nanometers, for instance, but without creating extra scattering from the edges, this is actually a big challenge for everyone, and I don't have the solution for this. But somebody who's better than us will find a way, I'm sure. But so still a long way to go. But another strong point of graphene is that we have this completely ideal conductor, two-dimensional. We can make many quantum devices, quantum tunneling devices. As a physicist, I learned many different tunneling devices in quantum mechanics. But those are all sort of theoretical or Gutangen thinking. But we can realize all these kind of devices using graphene. This is actually my dream in terms of this basic science. And we are trying to fabricate many graphene tunneling devices to realize these quantum mechanical devices. So, well, that's another interesting point from a science point of view. So, again, the challenge is all yours. And one of you guys will, can challenge this subject and probably solve these problems, and you will be the winner in the future in this area. Okay, at this moment, I'd like to close my talk and try to answer your question. Thank you.